I am the Philosophical Bachelor, and today I want to continue the second chapter, Cosmology, of my metaphysical investigations. Before we proceed further, we should consider another important premise in quantum mechanics, exemplified by Erwin Schrödinger's 1935 cat thought experiment. In a closed, opaque box, there is a cat, a flask of poison, a radioactive material, and a Geiger counter. If any radioactive decay is detected by the Geiger counter, even from one atom of the radioactive material decaying, the flask will be shattered, perhaps by a hammer mechanism triggered by the Geiger counter. This will then release the poison in the flask, which will kill the cat. While the half-life of a radioactive element is well established scientifically, it is only statistical. In a sample of any radioactive element, approximately half of the sample will have decayed during its half-life. However, we are unable to predict when any particular atom of the sample will decay. As verified by experiment, the probability of a radioactive atom decaying within its half-life is 50%. Whether an atom decays or not depends on what is happening inside the atom, making it a quantum mechanical process. In the nucleus of an atom, the neutrons and protons that constitute the nucleus are kept together by the strong nuclear force. This arrangement can become unstable as the protons shift within the nucleus, leading to repulsion between these positively charged particles that overcome the strong nuclear force, resulting in radioactive decay. Since the velocity and positions of these particles cannot both be known precisely because of Heisenberg's uncertainty principle, when a specific nucleus decays is random. Say the half-life of our radioactive source is 1 hour. Within 1 hour, there is a 50% chance that there will be radioactive decay, which will be detected by the Geiger counter, which then breaks the flask of poison which will kill the cat. If there is no radioactive decay, the cat remains alive. The idea behind Schrödinger's thought experiment is that while the opaque box remains closed, we do not know if the atoms of the radioactive material have decayed or not. The atoms are in a superposition of all its possible states. Its possible states, inter alia, are that it has or has not decayed. Superposition means that all possible states exist at the same time. The material has and has not decayed at the same time. That means that the flask and hence the cat are both also in superposition. The flask is both broken and unbroken. The cat is both alive and dead at the same time so long as the box remained closed. According to the Copenhagen interpretation of quantum mechanics, once the box is opened for an observer to see what is happening within it, this superposition of the possible states collapses to give just one state, which is the state that is observed. That is, the cat is either dead or alive. This accords well with our experience, since we never ever see a cat that is both alive and dead at the same time. However, the Copenhagen interpretation is not the only interpretation. There is also the many worlds interpretation, where the cat will be dead in one world, say our world, but alive in another world, with a whole new world born to accommodate the latter of the two possible states. Whenever there are logically possible and different paths for a quantum particle to take at a single point in time, entirely new worlds spring up, where in one world, one possible path is taken, and in another, the next possible path, and so on, a world for each possible path. So in the Schrödinger's cat situation, once the box is opened and observed, in one world, at least one atom of the radioactive material has decayed, releasing radiation that triggered the Geiger counter, hence breaking the poison flask and the cat is dead, and in another, no decay has taken place and the cat is alive. Whenever there is such a quantum fog, whole new worlds spring into reality upon observation, with just the difference in the latter case, a cat that is alive. This instantaneous springing into reality, since it requires the manifestation of entire new worlds in the flash of an observer's gaze. That is one way the many worlds interpretation can be operationalized. I can in addition think of two other ways. The second way does not involve the springing up of new worlds. In this way, there are many worlds already in existence, all identical in detail until a quantum fog arises, such as the decay of a single radioactive atom. To illustrate this idea, let us consider a world that has only one radioactive atom and nothing else, which can decay once before reaching a stable non-radioactive state. The time increment is the half-life, so Tn minus Tn minus 1 equals to T1 minus T0 equals to the half-life. Say it has decayed by time T1. In world 1, it has decayed, and since these worlds only contain one atom, that atom and that world has reached a stable state, with no more quantum fogs arising for that atom. Let us disregard the potential for virtual particles to arise, since that hopelessly complicates the picture. In world 2, 3, and so on, it has not decayed. At time T2, it has decayed in world 2 but not in world 3, and so on. At time T3, it has decayed in world 3 but not in world 4, and so on. Since there is always a possibility of 50% that the radioactive atom decays or not decay during its half-life, even in these worlds all containing only one radioactive atom, there is already a need for an infinite number of worlds just to be in accord with the many worlds interpretation. The third way involves the springing up of new worlds and relies on Berkeleyan idealism. These worlds have no physical reality, existing only as immaterial data implementations such as on a computer system, where each quantum fog will spin up a new world which copies and pastes the original world up to the point of the fog and then lets both continue on their separate ways. When the new world reaches another quantum fog, the process repeats. This idealism solves the material difficulty of the first way, which seems to violate the principles of mass and energy conservation and requires instantaneous creation of entire worlds. The second way requires there to already exist an infinite number of worlds to handle every possible quantum fog. Since even a world with one atom already requires an infinite number of worlds to handle all fogs, then the second way is tantamount to requiring a number of worlds larger even than infinity to the power of infinity. The third way resolves all these difficulties, but then faces all the challenges faced by idealism, such as why the world seems to obey laws and have regularity, when our idealist reality need not be bound by such limitations which arise because of the physicality of material reality. There is an obvious but trivial fourth way, which is that the many worlds interpretation is simply wrong. However, I do have a reason for raising it. If scientists can come up with such an extravagant theory and be taken seriously, then the many metaphysical theories concocted by thinkers over millennia should certainly not be sneered at, such as Plato's theory of forms, Spinoza's pantheism, Arthur Schopenhauer's will, Henri Bergson's Elan Vital, George Berkeley's idealism, Plotinus's one, the Tao of Taoism, and the cosmic or universal spirit proposed by mystics. I've outlined above two alternative cosmologies in modern physics of how the universe can develop from T-. In one, all matter and energy were already present, albeit concentrated in a dense singularity, which then expanded in the Big Bang, while in the other, there was the void, which had nothing, though the random fluctuations of quantum fields allowed virtual particles to arise, eventually leading to the manifestation of actual particles and energy, and then from there subatomic particles and then macroscopic entities. The latter may be a precursor of the former, an explanation for how there could have been matter and energy in the first place that later became concentrated in a singularity. Both theories are far less extravagant than the many worlds interpretation of quantum mechanics and reflect what we already know about the world, which is a world with many galaxies. Images from the Hubble telescope tell us that there are some 2 trillion galaxies in just the observable universe. Our galaxy, the Milky Way, is estimated to have over 100 billion stars. America's National Aeronautics and Space Administration estimates that there are 1 septillion stars, or 1 followed by 24 zeros, in the observable universe. Some of these stars will support a solar system of planets. Conditions conducive for the formation of organic life on planets include the presence of certain elements such as carbon, phosphorus, nitrogen, sulfur, and compounds such as water. There also needs to be an energy source, be it from the sun in the form of heat and light, or geothermal activity on the planet like underwater hydrothermal vents, to provide energy to organisms such as microbes and then later plants. There needs to be an atmosphere to keep terrestrial temperature in a narrow range and shield life forms from stellar radiation, and a reasonably stable environment so that any life forms that do appear can survive. The size of the planet is related to its mass and hence affects its gravitational acceleration. A planet too large will cause the weight of its objects to be heavy, hence requiring stronger biological structures for support. A planet too small may be unable to hold objects down such that no seas or atmosphere can form. There are many other necessary conditions, some of which may interact in complex ways. Because of the vast number of solar systems in the universe, each with different materials, organizations, and conditions, many trials are underway. Most of these trials will end up as worlds that have no life. Some of the rest of the trials will be in the sweet zone, where life is supportable, but yet that in itself is not sufficient to guarantee that life will emerge. Yet some of these will have developed low-level life forms, and then some of these low-level life forms may develop to become intelligent life forms. Those solar systems with life will be only a small proportion of the entire number of solar systems. But because the number of solar systems in the entire universe is a large number, the number of solar systems with life will be non-zero. We know that it is at least 1 since we are living in one such solar system. Since we have yet to find life elsewhere in all of our space explorations, we cannot conclude that there is any life elsewhere. Yet we are also unable to rule it out since the scale of our space explorations is extremely modest given the immensity of even just the observable universe. We may simply have not yet come across it. Despite its immensity, if the universe is finite, the possibility of the sweet spot may be so low that planet Earth may be the only instance of it. However, if the universe is infinite, this changes the picture radically because of the mathematics of infinity. Infinity multiplied by a non-zero probability still equals to infinity, unless the probability is infinitely small, in which case the answer is indeterminate. There is not much reason to think that the probability of the sweet zone is infinitely small, since firstly, we have an instance of it. Secondly, the conditions conducive to the formation of life are tough, but not impossible. Thirdly, the number of conditions is not unlimited. Hence, it is not just likely that there is life elsewhere in an infinite universe. Based on the mathematics of infinity, it is a certainty that there is life elsewhere at some point in time. In fact, the mathematics of infinity implies that there will be an infinite number of worlds with life. However, is the universe in fact infinite? The Big Bang Theory describes the formation of a part of the universe that has content such as atoms, planets, stars, and galaxies. According to John Paul Sartre, the ancient Greeks distinguished between 2 totalities. The first is cosmic reality as a totality, and the second is the first totality plus the infinite void surrounding it. If the universe is the entirety of everything, then it should follow the second definition of totality, to include both the part of the universe that has content as well as the void outside it that is cold and empty. Quantum field theory gives us a reason to include the void in our definition of the universe. Quantum field fluctuations cause virtual particles to pop in and out of existence everywhere, including the void, and hence the void's reality is not without content. The void is infinite because it is limitless. There is nothing bounding it, and so it extends infinitely. Yet, because virtual particles can come in and out of existence within it, this means that actual particles may at some point of time come to exist in the void. When this happens, the void is no longer a void. The void has become space. Since the void extends infinitely, so does space, since space is the void with some material content. That substantiates the spatial expanse of the infinity of the universe, but there is also its temporal infinity. As already explained, there is in fact no beginning of the universe. Even when it was the void which was characterized by nothingness, the void subsisted. And even if there ultimately is the big crunch which returns us to a singularity or whatever other cataclysmic event the scientists have postulated, such as black holes, consuming all of the material contents of the universe, there will still be that singularity or those black holes. Thus, not only does the universe exist eternally in the form of the void forever in the past of ancient T-, it will also exist forever in the future, even if it is in the form of a singularity or black holes, the void again, or in whatever form. Hence, the universe is infinite both spatially and temporally. The universe is the infinity of space multiplied by the infinity of time, which in the mathematics of infinity simply equals to infinity. This gives us our third principle. The universe is infinite spatially and temporally. How does this infinite universe then guarantee the existence of life elsewhere other than Earth? As more galaxies are formed and the existing ones continue to change, the conditions for the sweet zone may be met in those places also. In addition, virtual particles can occur anywhere in the infinite expanse of space. They may become actual particles via the second and third mechanisms I proposed earlier. Since there is an infinite amount of time for them to become more substantial, we can expect that new galaxies are coming into existence continually. These galaxies' configurations and hence motion vary, leading to different numbers of planets, stars, moons, orbits, momentum, collisions, and tides. They add to the number of trials and may generate novel conditions for the formation of life. In addition, each of these galaxies is effectively different worlds and may have altogether different physics from our world because they may have different fundamental physical constants. In 2011, scientists discovered that the fine structure constant, alpha, is not actually constant when they pointed powerful telescopes in different directions of space. Approximately 1/137, the fine structure constant is the strength of the electromagnetic force governing how electrically charged elementary particles and light interact. Because it is small, electrons in atoms, when energized, can hop away from its parent atom to form chemical bonds with other atoms and molecules. If it is bigger, electrons will require more energy to make these hops, and stars may not be able to create carbon, which is the basis of life on Earth. Hence, if indeed fundamental physical constants vary across the universe, different parts of the universe may have different physics, leading to different kinds of matter, energy, and possibly biologies from those we are currently aware of. Are dark matter and dark energy examples of this? I talked about trials. The universe, with its vast variations of solar system configurations, is akin to a laboratory with a correspondingly large, if not infinite, number of trials running. However, this metaphor has limitations. Laboratory trials are carried out to test a clear predefined hypothesis by an intelligent agent. Those who want to hold that the same applies to the universe, that there is a divine agent who is using the universe as a massive laboratory, will then have to admit that this agent is not omniscient, since an all-knowing deity will not need to experiment by trial and error to figure out how things can develop. Otherwise, they will have to explain why their God created a very large, if not infinite, universe, only for most of it to be barren. If the universe was instead limited, Giordano Bruno questions why an infinitely powerful God will make a merely finite universe, and why he did not create life everywhere instead of on just one planet. The notion of trial suggests that there is no divine omniscient intelligence or agency at work, at least not in ancient T-, and even for a long time after T0. What is going on in the universe resembles a cross between the infinite monkey theorem and Jorge Luis Borges' short story, The Library of Babel. Given enough time, it is a statistical certainty that an infinite number of monkeys pounding on typewriters will produce all possible books that could ever exist. Such a library will contain all propositional truths, but these will be swarmed by greater numbers of untruths and even greater mountains of gibberish. Borges writes, "For every rational line or forthright statement, there are leaks of senseless cacophony, verbal nonsense, and incoherency. It is a feverish library, whose random volumes constantly threaten to transmogrify into others so that they affirm all things, deny all things, and confound and confuse all things, like some mad and hallucinating deity." Like our infinite universe, Borges recognizes the pessimistic implications of such a library. All the generations of mankind could pass before the dizzying shelves ever reward them with a tolerable page. While Frank Drake's equation points out that life elsewhere in the Milky Way, no less the universe, is likely, Enrico Fermi questions why, in that case, we have not encountered them not only in their bodily form, but also in the form of any structures they had built or signals they had transmitted. Even the Milky Way alone is extremely vast, and humanity has explored precious little of it in the form of space flight or even just through telescopes. Hence, a major reason why life elsewhere has not been discovered by us is that despite how tremendous we may consider our efforts to be, we have simply done too little space exploration work so far. Planets, moons, asteroids, and stars are but just so much dead dust, swirling in infinite tapestries of galaxies, which themselves swirl as their masses exert gravitational forces on one another. Everything that has happened in the universe up to this point has been portrayed by me as so many acts of cosmic chance, accidents that led up to whatever it has led up to across infinite worlds. Even gravity can be explained by cosmic chance. Say there are various worlds in which the universal gravitational constant, big G, varies, the way the fine structure constant seems to vary. In worlds where G is too small relative to our galaxy, small bodies do not coalesce, and hence no bigger bodies such as planets and stars can form. We probably do not even recognize these worlds as worlds, since whatever is in them do not seem to form a system. In worlds where G is too large, the bodies coalesce continuously, creating one massively heavy body which collapses under its own weight, resulting in a black hole. It is only when G is the value we know it to be, 6.6743 times 10 to the minus 11 meter cubed per kilogram second squared, that galaxies appear as they do to us, with large bodies formed from the coalescence of smaller ones, and stars from such coalescence and compression leading to nuclear reactions. Did the Big Bang spawn the many worlds of the universe, Or is it just an occurrence in one of many worlds, one among the many trials in the universe? Please join me again next week when I read the next chapter 3 on life. Thank you for listening to the Philosophical Bachelor.